Hello and welcome. This is video 1 of 3 for Deep Learning Unit 2. In this video we become model doctors, will diagnose the two great failure modes overfitting and underfitting, learn the 6 standard cues, understand hyperparameters and validation sets, and master the bias-variance trade-off with famous dartboard picture. We end with a quiz on the most common diagnosis in all or machine learning. Let's begin. Hello everyone and welcome to Unit 2 of our Deep Learning course. This is the bridge unit and my favorite to teach. In the first half we become model doctors, we'll learn to diagnose WHY models fail overfitting, underfitting, bias, variance and how we estimate parameters from data. And in the second half we finally build an actual neural network, from a single brain cell all the way to backpropagation, the algorithm that makes it learn. By the end of this unit you'll be able to narrate exactly what happens when someone types model.fit. Let's get started. Here's our roadmap, 2 big parts. Part 1, Machine Learning Basics, Overfitting and Underfitting, Hyperparameters and Validation Sets, Estimators, Bias and Variance, Maximum Likelihood and Bayesian Statistics, and the 8 challenges that motivated deep learning in the first place. Part 2, Deep Feed-Forward Networks, the biological neuron and its artificial twin activation functions, the famous XOR problem that froze AI research for a decade, and the full training loop, forward propagation, loss, backpropagation, and gradient descent. Diagnosis first, construction second. Let's go. As always, let's be clear about what you'll be able to do by the end. You'll diagnose overfitting and underfitting just by looking at training and validation curves and know the right cure for each. You'll distinguish parameters from hyperparameters and explain why validation sets exist. You'll compute point estimates and reason about the bias-variance trade-off. You'll explain maximum likelihood versus Bayesian estimation. You'll list the challenges that motivated deep learning. In the big one you'll trace one complete training loop of a neural network, forward pass, loss, backpropagation, weight update. Screenshot this slide. It's your self-test for the end of the unit. Part 1, Machine Learning Basics. Let me give you the theme of this whole chapter in one line. Generalization is the entire game. A model is only as good as its performance on data it has never seen. Here's the story we'll follow. A student memorizes every past exam paper, word for word, and fails the real exam the moment the numbers change. That student is an overfitted model, and understanding that failure, measuring it and curing it is what the next hour is about. We'll cover fitting, bias and variance, estimation, and finish with why all of this pushed the world toward deep learning. So generalization? What every machine learning model is actually trying to achieve. Overfitting and underfitting are the two main problems that degrade model performance. And both are defined against one goal: the model must produce reliable, accurate output on unknown, unseen inputs. That ability is generalization. Back to our 2 students. One memorizes every past paper answer perfect on practice, useless on anything new. That's overfitting. The other barely skims the chapter headings, fails everything, practice included. That's underfitting. The good student learns the method and passes questions they've never seen. That's generalization. Keep these 3 students in mind, the whole chapter is their story. Let's meet failure mode number 1 properly, overfitting. Overfitting happens when the model tries to cover all the data points more than required. In doing so, it starts catching the noise and the errors in the dataset, not just the signal. Accuracy on new data collapses. Picture the regression graph. Instead of a clean best fit line, the curve wiggles desperately through every single scatter point. It looks impressive and it's useless, because there's no best fit at all, just memorized coordinates. The technical signature: remember this pairing. Overfitting means LOW, bias, high variance. And here's the counterintuitive part: the more you train, the more likely you overfit. Training longer isn't always better, a fact that will justify early stopping in a few slides. My favorite example: a house price model that learns house number 3172 with the red door costs 82 lakhs. Perfect memory, zero understanding. So how do we fight overfitting? Here's the standard toolbox: 6 cures, and this list is a guaranteed exam question. 1. Cross-validation: rotate which data you hold out, so every point takes a turn as the test. 2. Train with more data, enough examples, and the model simply can't memorize them, all the noise gets swamped. 3. Remove features, fewer inputs means less freedom to fit noise. 4. Early stopping, quit training just before memorization kicks in. 5. Regularization, penalize large weights to keep the model simple. Unit 3 is entirely devoted to IS1. And 6. Ensembling, combine several models so their individual quirks cancel out. Quick thought experiment: if collecting data were free, which would you reach for first? More data. It's the cure with no side effects. Failure mode number 2: underfitting the mirror image. An underfit model hasn't learned the patterns even in the training data. And that's the diagnostic tell. So let me highlight it. Underfitting is bad everywhere: bad on training data, bad on new data. Overfitting is good on training, bad on new. One check of the training score tells them apart. The signature pairing: high bias, LOW variance, the exact opposite of overfitting. Why does it happen? The model is too simple, the data is noisy or uncleaned, the training set is too small, or training was too short. The classic picture: fitting a straight line to clearly curved data. No amount of extra training fixes it, a line cannot bend. The cures: increase model complexity, add features, clean the noise, train longer. Between the two failures lives the target, the good fit. And finding it is beautifully practical. Watch the model's error over time as it trains. In the beginning, error falls on both the training data and the test data. The model is learning genuine patterns. But if you train too long, the model starts learning the noise, and while training error keeps falling, test error turns around and starts rising. That turning point is the sweet spot. The rule: stop training just before the validation error starts to increase. My kitchen analogy: toasting bread. Too short, pale and underdone. Too long, burnt. You pull it out at golden brown, and in machine learning the validation curve is how you watch the color. Sketch this picture once by hand: falling training curve, U-shaped validation curve, and you'll never forget it. It's arguably the most examined diagram in applied machine learning. Let's compress everything so far into one table: your revision card for fitting. Training error: underfitting high, good fit low, overfitting very low, suspiciously close to zero. Test error: underfitting high, good fit low, overfitting high. There's the trap: great training numbers, terrible reality. Bias and variance: underfit high bias, low variance. Overfit low bias, high variance. Good fit balanced. Complexity: too simple just right, too complex. And the practical diagnostic you'll use in every lab: look at the two errors together. High underfit, low overfit, low ship it. Photograph this table. Now a distinction that sounds bureaucratic but is actually fundamental: parameters versus HYPR parameters. Parameters are learned by training the weights and biases. Hyperparameters are the settings we choose before training, the learning rate, the number of layers, the number of epochs, the regularization strength. Here's the subtle question: why can't we tune hyperparameters on the training set? Because the training set always votes for maximum complexity. More capacity always fits the training data better. Tune there and you've built an overfitting machine. The solution: carve out a validation set, train on the training set, tune hyperparameters on validation, and touch the test set exactly once at the very end. A typical split: 80-10-10. My cooking analogy: you adjust the recipe by tasting from the pot, that's validation. But the dish is judged by a guest who never entered the kitchen. That guest is your test set. Let them into the kitchen and their opinion is worthless. New concept block: estimation, because everything a model does is ultimately a sophisticated guess. An estimator is a function or algorithm that estimates the target quantity from data. Point estimation means providing the single best prediction, or that quantity: one number, one best guess. What can we estimate? A single parameter, a whole vector of parameters like all the weights of a regression, or even an entire function. The notation, which follows us for the rest of the course: theta is the true value, usually unknowable. Theta hat, theta wearing a little hat, is our estimate computed from data. Hat means made from data, and here's the perspective shift. Every trained neural network is one giant point estimate, millions of theta hats, our best guess at the function from images to labels. An opinion poll estimating a vote share, same mathematical creature. Two tiny worked examples to make estimation concrete. Example 1, we want the average exam score of all students in a school, but we can only sample 5 of them. Their scores 78, 85, 90, 82, 75. Average them, 82. So mu hat equals 82 our point estimate of the true school-wide average. Example 2, it rained on 12 of the past 30 days. Point estimate of the probability of rain 12 over 30 0.4. Simple, right? But now the crucial observation. Sample 5 different students, you get a different average. Watch a different month, a different rain probability. The estimate wobbles from sample to sample. Is 82 the truth? No, it's a guess. And quantifying the quality of that guess, how far off, how wobbly, is exactly what bias and variance measure. Next 2 slides. Quality measure number 1, bias being systematically off target. First, the big picture errors split into reducible and irreducible. Bias and variance are the reducible part, the part good modeling can shrink. Bias is the gap between the model's expected prediction and the actual value. The formula, bias equals the expected value of y hat minus true y, in words, average all your predictions. How far is that average from the truth? The perfect analogy, a bathroom scale that always reads 2 kilos light. Weigh yourself 100 times, average the readings, still 2 kilos wrong. Consistent but consistently wrong. That's bias, an error that averaging cannot wash out. Low bias, few assumptions, model hugs the training data. High bias, too many assumptions, model can't even match training data. Hello, underfitting. To reduce high bias, use a more complex model, add features, ease off regularization, get more data. Quality measure number 2, variance, the wobble. Variance measures how much the model's predictions change when trained on different parts of the training data. The source book's example is perfect. Train the same model 3 times on different random splits. Same input, 3 predictions, 80, 90, 100. The model changes its mind depending on which data it happened to see. High variance. Now the second scale, it reads 71.9, 68.2, 70.4 for the same person. RIGHT on average, wildly unreliable per reading. Notice, this scale and the biased scale fail in opposite ways. The connections, low variance with high bias, underfitting. High variance, great on training, poor on test, overfitting. Bias and variance are the fitting story retold in the language of error. And now the picture that makes bias and variance unforgettable, the dartboard. Every dart is one model trained on a different data sample. Where do the darts land? Low bias, low variance, darts clustered on the bullseye. Accurate and consistent. The good fit. The dream. Low bias, high variance, darts scattered all around the bullseye, right on average, unreliable individually. That's overfitting. High bias, low variance, darts tightly clustered, in the wrong spot. Consistently wrong. Underfitting. And high bias, high variance, scattered and off center. The worst case, usually a broken pipeline. Here's the trade-off at the heart of all machine learning: adding complexity lowers bias but raises variance. The art is finding the balance, which is exactly the good fit sweet spot from earlier. 1 story, 2 languages. Quiz time. Question 1, and it's the single most common diagnosis you'll ever make in practice. A model achieves 99% accuracy on training data, but only 62% on the validation set. What's the diagnosis, and which is a sensible fix? A. Underfitting, add more layers. B. Overfitting, high variance, add regularization or more training data. C. High bias, remove features. D. Good fit, deploy it. Look at that 37-point gap and think about our table. Pause the video and make the call. The answer is B. Overfitting, and the fix is regularization or more training data. The reasoning: great on training, poor on unseen data, is the textbook overfitting signature, the model memorized noise. Low bias, high variance. Why not the others? Option A, diagnosis underfitting, but an underfit model would be bad on the training data too, and adding layers would add capacity and make the gap WRSE. Option C is backwards for the same reason. And option D, deploying a model with a 37-point generalization gap. Your users would meet the 62%, not the 99. Remember the 2-number diagnostic: high underfit, low overfit, low ship it. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.